Hello learners, welcome to this video lecture on Thermal Energy Conversion System Module 1 of Energy Engineering, presented by myself, Ranjit PK, Assistant Professor, Department of Mechanical Engineering, Global Academy of Technology. In this video lecture, we are going to understand about a review of energy scenario in our country, the general philosophy and the need for energy. Then we look at the various thermal energy conversion system, that is the different types of fuels used, the equipments used for burning the coal, the stokers and its different types, then the oil burners, then the advantages and disadvantages of using the pulverized fuel, the various equipments used for preparation and burning of the coal, then the various fuel furnaces used, then further the coal and ash handling system, then we look at the generation of steam using various methods of boilers. We look at chimneys and its types, then calculations involving the height and to produce a given draft, then look at the cooling ponds and towers, then accessories used for the steam generation. So let's begin learning. If you look at the energy scenario, energy has always been the major input for the economic development of the country, and this economic growth always depends on the long-term availability of the energy, and this energy should be very inexpensive, easy to get to, that is, it should be easily available and it should be eco-friendly. As on March 2020, our country's installed capacity stands at about 3.7 gigawatt, that is 3,70,000 plus megawatt, and coal has been the biggest contributor for this, amounting to 53%, renewables accounting to about 24%, nuclear 2%, then the gas form in 7%, then diesel amounting to 0.1%. I have a video which shows the history of energy and its evolution.
1.5 million years ago, a spark lit the first human-made fire and ignited a great revolution for our species, a revolution of energy. Our ancestors first used energy by burning biomass, like wood, to create fire. Fire was eventually controlled and used to cook food. Cooking breaks down food quicker than a primate's digestive system and allows for a greater intake of calories in a shorter amount of time. This extra nourishment enabled our energy-intensive brains to grow larger. Extra time, previously used for foraging and eating, could now be spent on more cerebral tasks like thinking, socializing, and creating. In 6000 BCE, early humans created a thermally insulated chamber used for drying and hardening clay, known as a kiln, which became a common technology. By burning biomass and generating temperatures in excess of 900 degrees Celsius, humans could now create pottery, tiles, and bricks. As technology advanced, kilns became hot enough to melt metal. Humans eventually pioneered metallurgical studies, the science of metals. In 3200 BCE, civilizations in places like the Middle East, Asia, and Europe discovered that the smelting of copper with tin created bronze, a hard, durable alloy. This technological leap gave life to the Bronze Age, an age which fostered trade, agriculture, and the first intermingling of cultures. While early kilns were hot enough to melt copper and tin, advancements were needed before they could melt iron, a stronger, more abundant metal. It was also discovered that infusing iron with carbon resulted in a high tensile alloy known as steel. In 1200 BCE, steel transformed civilization and moved humans into the Iron Age. The Iron Age was a period of lighter, sharper weapons, armored cavalry, and more resilient tools. Today, steel remains one of the foundational building blocks of our modern society. In 300 BCE, humans harnessed the energy of flowing water. Water wheels were used for drawing water from rivers to fill aqueducts, irrigate farmland, and to mill flour. Energy in wind was later captured using windmills starting in 900 AD in Persia and independently in Europe. Wind energy was primarily used in granaries for powdering grains into flour used for cooking and baking. In the 1800s, mankind saw a second energy revolution. a revolution as transformational as first harnessing fire: the use of fossil fuels. The first major fossil fuel, coal, saw demand soar during the Industrial Revolution as a flurry of new mechanical and electrical technologies emerged. From steam engines to electric turbines, the world was transformed with industrial machinery and communication. For the first time in history, humans could travel at speeds greater than a horse on land and faster than the winds at sea. About the same time, natural gas was discovered and used in Britain and the United States for additional lighting in the evenings. This extended the hours of human productivity deep into the night. As a result of the technological and energetic changes from the Industrial Revolution, household incomes rose across the world and populations boomed. The coal-powered steam engine was eventually overtaken by the oil-powered internal combustion engine during World War I. Sir Winston Churchill and the British Navy opted to replace its steam-powered battleships with oil-powered ones, which were faster and more maneuverable. This technology gave Britain a significant military advantage over the Germans, who were using the now outdated steam-powered ships. This switch from coal to oil has been argued to have been the deciding factor in World War I. It clearly cemented oil as the most important commodity on Earth. Oil was later harnessed for things like plastics, asphalt, commercial aviation, and space travel. While the First World War gave rise to oil, the Second gave rise to nuclear. After Albert Einstein's famous equation, E equals mc squared, demonstrated the colossal quantities of energy inside an atom, the scientists and engineers of the Manhattan Project unleashed the power of the atom with 2 nuclear bombs dropped on Japan. That atomic energy was later harnessed to boil water into steam, which could spin turbines to generate electricity. The future is unknowable. Creating and focusing energy and the discovery of new energy sources has been the genesis for technological advancement. Thomas Edison didn't create the light bulb from an incremental improvement of the candle, but neither has electricity replaced the need for fire. Our ancestors, who first learned to harness fire, could not imagine their descendants using fire to travel to the stars. As we weigh the benefits of a fossil fuel-powered society with its long-term drawbacks, like scarcity and climate change, the future remains uncertain. With increasing global populations and rising individual energy needs, the only certainty is we will use more energy tomorrow than we do today.
So, the key takeaway from this video is that right from the civilization when man first began, the use of energy has been progressive and has always been in demand. If you look at the need for the energy as the years have progressed, you look at this animation, the demand has always been increased and it has become a vital component for the nation's economic progress. Increase in the population has also increased the energy requirements, and the industrialization also added to this. The transformation of the civilization to the present day, what we have, is always been dependent on the progressive use of energy, and thus we can say that the need of energy use and the availability of the energy is always ever increasing. We now look at the various aspects of thermal energy conversion system. This is predominantly dealt in a steam power plant. The steam power plants are the power plants which produce 60% of the total power requirement in our country. Here, thermal energy is used to raise the steam, and that steam is used to run the steam turbines to produce mechanical energy. This mechanical energy in turn is converted into electrical energy, and steam power plants are suitable for a large scale production of electrical power. The steam power plant essentially uses fossil fuels to generate steam. So the selection and the selection of the fuel depends on the availability of the fuel and the various economic conditions. There could be different types of fuels that could be used for steam generation, including the solid, liquid, and the gaseous fuels. In case of the solid fuel, coal is the major fuel used for thermal power plants to generate steam. Coal is found to generally occur in nature, which was formed by the decay of the animal and vegetable matter buried under the earth millions of years ago. If you look at the chemical substance, it contains about 50 to 90% of carbon and other forms of chemicals. There are various types of coals that are used for steam generation. It could the first form being peat, lignite, bituminous, then anthracite. As the coal content varies or as the type varies, you could see that there is increasing heat levels and increasing the carbon content values, and the moisture content is getting decreased. And it is found usually that either the soft coal or the bituminous coal or the anthracite coal is the most widely desired fuel that is to be used in a steam power plant. In case of a liquid fuel, the liquid fuels are usually derived from the crude petroleum and its byproducts. The petroleum or the crude oil is again consisting of 80 to 85% carbon and the other compounds. The fractions vary from light oil to heavy oil in the order of naphtha, gasoline, kerosene, diesel, and finally the heavy fuel oil. The heavy fuel oil is the most desirable used type of liquid fuel that should be used for the generation of steam. In case of gaseous fuels, either natural gas or manufactured fuel, gaseous fuel, that is the artificial gaseous fuel is used. However, it is generally seen that the manufactured gases are little costlier than the natural gas, and amongst the natural gas, it is usually pretty easily available and is abundant in nature, and this is usually obtained in gas wells and the petroleum wells. The major constituent of the natural gas is methane, containing about 60 to 65% carbon and small amounts of hydrocarbons. The natural gas should be transported from the source to the place of the use through the pipes, and this distance could be very small to several 100 kilometers. This natural gas is colorless, odorless, and usually non-toxic, and its calorific value ranges from 25,000 to 50,000 kilojoules per meter cube. When compared to the solid fuel and the liquid fuel, this is pretty less. However, the attempts have been made to produce the gas from artificial means, usually including the producer gas, water gas, coke oven gas, and blast furnace gas. But the commercial application of these artificial gases that are produced for a power plant is not found. The gaseous fuels have advantages similar to those of liquid fuels, except for the storage issue. However, the major deterrent for the power plant using a natural gas is that the availability of the natural gas, and it is desired that the power plant be set up near the source. Otherwise, the transportation losses would be very high, or the transportation cost would be very high, and hence we don't get to see many gaseous fuel based power plants. So, coming to this understanding the various types of fuels, we now understood that amongst the solid, liquid, and gaseous fuels, the solid fuels are the major candidate, that is predominantly the coal. So all major steam power plants run by burning the coal. Coal henceforth will be referred as fuel, which is either in solid or powdered form. And if the coal is in powdered form, it is usually known by the term as pulverized coal. And any economical working of a steam power plant depends on combustion, and this combustion should be efficient. Hence, the fuel feeding and the firing system plays a very important role for the combustion to happen. And almost 50 to 60% of the total operating costs involve with the fuel purchasing and the fuel handling. So the fuel system should be designed in such a way that based on the type and nature of the fuel, the system is available for use. So if you look at the various fuel handling stages, it starts from coal delivery, where the coal is delivered from the source, then it is unloaded, then it is prepared. So there is some amount of preparation needs to be done before the coal is started to use. Then this prepared coal has to be transferred, then it should be stored. By transfer, we mean transfer it from the storage to the power plant. Then within the power plant premises also there is some amount of outdoor storage usually involved, and it starts with the cover storage as well in case of uh, rain or water being a major deterrent. Then within the plant it should be handled well, and then it is weighed and measured, and in the right proportion it is then used for firing. So a small video which explains you what is the fuel handling system.
Coal Handling System, Kakinada Port, India. The multi-purpose maritime port of Kakinada, located in the Bay of Bengala on the eastern coast of India, was commissioned in November of 1997 by the state government of Andhra Pradesh. Within the port enlargement works, the Indian port operator Bothra Shipping Services awarded the construction of a coal handling terminal to Duro Felguera on a turnkey basis that would enable the port to handle 8 million tons of coal per year. Coal is unloaded from the vessels at the seafront of Quay Number 5, which, equipped with an operational 14-meter draft berth, can receive Handymax and Panamax vessels. Two different systems are used for unloading: harbor mobile cranes and vessel gear cranes. Harbor mobile cranes are positioned aside the vessel to unload the coal into large capacity track hoppers. The terminal is also equipped with several coal conveyor belts. Line 1, coal unloading at the quay and coal stacking with one of the yard machines. Line 2, direct dispatch by unloading the coal at the berth and wagon loading or coal stacking on the blending area. Line 3, coal reclaiming with one of the yard machines and wagon loading or coal stacking on the blending area. Handymax vessels use their own cranes, vessel gear cranes, to unload the stock into smaller-sized mobile hoppers, which feed the berth conveyor belt by means of a belt feeder. The conveyor belt is installed between the rails of the hoppers, and it is equipped with a scale to measure the material flow and a metal detector. It also has an inline magnetic separator that removes undesired metal particles from the material flow in order to avoid tearing and other damage to the belt. When unloaded on the berth conveyor belt, the coal is conveyed all the way to the stacking area, crossing the sea on elevated or raised galleries. All conveyor belts are well covered with canopies to minimize dust emission or material loss in the event of the wind blowing. Once in the stockyard area, the material flow may be diverted into either of the two main conveyor belts in the stockyard, as selected by the operator of the terminal. The stockyard has a maximum capacity of 1,100,000 square meters, of which 220,000 square meters are assigned to blending operations that vary depending on the requirements of the end customer. The stockyard is equipped with a water dust suppression system at all the transfer points of the belt conveyor system, and water sprinklers fitted at both sides of the coal stockpiles. The stacking operations are basically performed by means of two stacker reclaimer machines. These machines can stack the coal from the berth in trapezoidal cross-section piles, or reclaim the coal from said stacks as required. The material reclaimed by the stacker's reclaimers is conveyed to the dispatch area, where it is loaded onto wagons using machinery specifically designed for that purpose. This machine is capable of loading complete train rakes of up to 58 wagons in approximately 2.5 hours. Alternatively, this machine can also operate as a stacker, thus enabling various kinds of coal to be blended in the pile nearest the train tracks. The terminal is entirely controlled from a control room located on the stockyard at the sea-facing front for better supervision of the operations both at the berth and at the stockyard.
So the video showed about how the coal is delivered, how it is unloaded, and how it is prepared and then transferred. So the transfer happens through the railway wagons, and then it is taken to the site where it needs to be used. So you look at, have a close look at the video, just observe what are they doing here. So reflect for a moment what just happened here. If you had closely looked at the video, the people here were basically picking up the stones from the coal which is presented to the stockyard, so which is basically a form of preparation. So this is what they were doing. They were preparing the coal by basically transferring it, basically picking up the impurities. So if you look at the fuel firing mechanism, it could be classified as a fuel hand fired, stoker fired, and pulverized fuel fired. If in case of a hand fired mechanism, it is a smaller size boiler that is usually operated by a hand firing mechanism. Here coal chips are put into the furnace frequently by shovels, and this system was the one which was used to drive the coal engine locomotives in the past, and it is not used anymore. Though why? Because though this hand firing is very simple and cheap, it has low combustion efficiency, and in case of any load fluctuations, it is very slow in providing its response. And the biggest disadvantage here is the combustion control is very difficult, because once the coal is put into from the shovel into the boiler, the combustion cannot be controlled, and it is suitable only for the small scale power plants. In case of a stoker fired mechanism, it is a stoker is nothing but a fuel burning mechanism used for burning the fuel on a grate. Although slightly costlier, these are generally used to feed the solid fuels in most of the power plants, and the combustion is found to be more efficient here when compared to the hand fired mechanism, and the fuel handling system is automatic and there is faster response to the load fluctuations. There are various classification of a stoker fired. It is classified as overfeed and underfeed stoker, and the overfeed stoker is again classified as traveling grade stoker and spreader stoker, and the underfeed stoker as a single retard stoker and a multi-retard stoker. Before we understand the subclassification of this, we understand what is the principle of an overfeed stoker. In this overfeed stoker, the primary air enters the grate from the bottom as shown here, and which cools the grate also while moving up, and this air gets heated as it passes through the hot ash bed, and the coal supplied to the grates on above the point of air of admission, hence the name overfeed. So meaning air is supplied at the bottom and coal on the top, whereas in the underfeed mechanism, coal is fed underneath from the grate. There is a tires through which the coal is fed, and the air is also supplied from the bottom. So essentially the direction of the fuel and the air is same, and this is very suited for burning semi-bituminous and bituminous coals, which usually have high volatile matter. So having understood how the feeding mechanism works, we now look at how a traveling grate stroker works. So in this traveling grate stroker, there is a coal hopper having an adjustable gate. So this adjustable gate can be moved forth, and the amount of coal that is supplied for the burning is varied. So the coal from the coal hopper is made to fall onto the grate, that is a chain grate, it keeps moving, and there is primary air supplied at the bottom through the primary air ports, and the moment the fuel is in contact with the air, it gets ignited, and the heat is then liberated, is sent to the boiler, and then it is used for the further process. The exhaust is then let out to the chimney, and the coal which is burnt also produces ash, which is collected at the this end, at the end of the grate, and is then sent to further processing as well. As the grate travels here, the coal is also which is also on the grate for travels, hence the name traveling grate stroker. This is shown by an animation in a video here. So this is how it works basically. This is the adjustable gate. The ash that is collected. And then from the boiler it is let out to the chimney. This is the chimney through which the exhaust comes out. That is how our traveling grate stroker works. The next one is a spreader stroker. The same mechanism. In addition to the traveling grate stroker, there is a spreader. What it does is basically, you can see in this animation, it ensures that the coal that is fed is spreaded evenly onto the grate that is traveling. So there is the combustion happening uniformly. All the coal that is spreaded onto the stoker participates in the process of combustion, and the efficient fuel efficient firing mechanism is thus produced. In case of a underfeed mechanism, it is a single retort stoker where the fuel is placed in a large hopper shown here, and then it is rammed. So basically there is a reciprocating action here. There is either a screw conveyor or a reciprocating ram which rams the coal and pushes onto the retort, and air is supplied to the tires that is provided along the upper edge of the grate. So from the retort there is the air. There are pushers placed at certain distances so that the coal that is fed onto the retort is pushed evenly onto the retort here, and it burns. And the coal burning capacity of a single retort stoker varies from 100 to 2000 kg per hour. In case of a multi-retort stoker, as the name suggests, it is the multi-retort. It consists of a series of alternate retorts and tire boxes of supply of air, as shown here. You can see many systems. So each retort is fitted with a reciprocating ram for feeding and the pusher plates for uniform distribution of fuel. So the coal is pushed into the each respective reciprocative rams and then is provided for the combustion. The number of retorts vary usually in the order of 2 to 20, and the burning capacity is better than a single retort stoker with the value varying from 300 kg per hour to 2000 kg per hour per retort. So you can imagine, in case of a single retort, it is 100 to 2000 kg per hour in a single retort. Here it is 300 to 2000 kg per hour in a single retort. So for example, if there are 20 number of retorts, so it is 20 into 2000 kg for every 1 hour, that the amount of coal that is fired. So you can imagine the amount of coal firing that is happening in this. The next form of coal firing is a pulverized coal firing. Pulverizers are basically devices that are used to produce the coal in the powder form. Here the coal is grinded into a fine powder with the help of a grinding mill. The main purpose of this pulverizing the coal is to increase the surface area of exposure to the combustion, which usually results in faster and more efficient way of combustion. The efficiency depends on the size of the coal particles. The coal powder that is pulverized here is in the order of about 6 to 8 mm. A video which shows this.
In recent times, pulverized coal has emerged as the most widely used fuel in the steel rerolling mill sector. However, in order to get the optimum output, it is important that the supply chain of coal is properly maintained. The coal typically used in the SRRM sector is characterized by high ash and low calorific content. This leads to premature cracks and failure of the refractory lining. Ash deposits require more heat to be added to the charge for attaining the desired temperature, thus increasing burning losses. Also, high ash content leads to choking of the recuperator tubes. This necessitates frequent cleaning, thus high maintenance cost and reduced performance of heat exchangers. The ideal size of pulverized coal should be at least 75 to 80% of 75 microns. In the conventional systems, fine coal ranges from only 10 to 30% of 75 microns. Non-uniform coal particles undergo partial combustion and result in deposition on the furnace walls. These coarse particles escape from the furnace with flue gas in the form of unburnt carbon or ash. The energy-efficient alternative to using pulverized coal as fuel starts with the procurement of good quality coal. Coal with high calorific value and low ash content, for example, Assam coal is the most ideally suited for use as pulverized coal. The next step is to process or pulverize the coal into the desired fineness consistently. To do so, certain modifications in the pulverizer are required. The critical components of a pulverizer are a hammer, a mild steel liner, a classifier, and an inbuilt blower. For better and long-lasting quality of pulverizer, the metallurgy of the hammer should be improved to increase its resistance to wear and tear. The suggested additions to be made while casting of the hammer consists of manganese 13%, carbon 1.13%, silicon 0.4%, sulfur 0.003% and phosphorus less than 0.2%. Proper dimensions and thickness are to be ensured in the classifier. Grooved EN31 hardened steel plates or casted high manganese should be used in the liners. This will help achieve 65 to 80% of the desired 75 microns. The performance of a coal pulverizer can be gauged from the size and uniformity of the coal output. Let's take an example of a 10 TPH rolling mill to understand the economics. Typically, a furnace will have an annual fuel consumption of 3 crores 24 lakh rupees. With the use of energy efficient system, the savings in specific fuel consumption shall be about 15%, which implies savings of rupees 16.2 lakhs annually. The modified pulverizer will entail an investment of 7 lakh rupees. Thus, the investment can be recovered in less than 5 months. For ensuring optimum performance, a pulverizer should be regularly maintained. The pulverizer components should be replaced periodically. It is proposed that a bomb calorimeter be used for in-house quality checks of coal. A metal sieve of -200 mesh size or 75 microns can be used for measuring the coal output.
So the key takeaway from this video is that the pulverizing has formed the basis for many coal power plants being operated upon, and the pulverized coal firing also leads to an energy efficient usage of the system. The pulverized coal firing system could be either a unit system in which each burner of the plant has its own pulverizer and its handling unit, or it could be a centralized or a central or bin system where the fuel is pulverized in the central plant and then the pulverized fuel is distributed to each burner, and then various types that are usually used include ball mill, ball and race mill, impact or hammer mill and the bowl mill. In the unit system, as I mentioned before, each burner has its own pulverizer. There are a number of units required to be attached, which depends on the capacity of the boiler. Here the raw coal is from the hopper is fed to the pulverizing mill through the feeder. The hot air is then passed through the feeder to dry the coal before it is fed to the pulverizer. So any moisture content here is then removed. The pulverized coal is then carried from the mill with the help of an induced draught fan. So the induced draught fan sucks and pushes this coal into the further process. There is secondary air that is supplied to the burner, helps in creating the turbulence and ensuring that the additional air is supplied for the combustion process to be complete. In case of a central system, the crushed coal is dried using the same mechanism is the same. The only difference here is in case of a unit system, it is given to the each boiler burner or each furnace burner, whereas here it goes into a feeder and from the feeder it is provided to the burners. So there could be many systems of usage of boiler or a burner, and through the centralized storage bin, the pulverized coal is fed to each of these burners. So in case of a ball mill, what happens is it consists of a large cylinder which is partly filled with various sizes of steel balls. So within this drum there are steel balls that are usually filled as seen in this animation. The cylinder is rotated at a certain velocity, and the pulverization takes place because there is a result of action between the balls and the coal. You can see the green represents the coal here, and then it is fed to the rotating drum, the silver ones being the steel balls. So the hot air from the preheated air is mixed into the pulverizer. So the streams of the air pick up the pulverized coal and pass through the classifier. So the output is essentially controlled by the dampers, which is located at the exhaust, and varying the flow of the air and controlling the rate of the fuel could be possibly achieved. So a ball mill is capable of pulverizing 10 tons of coal per hour, and it consumes about 20 to 25 kilowatt of energy per ton of coal that is supplied. In case of a ball and a race contact mill, there are spring actions. There is springs which is used to hold the upper race, and this provides the force that is needed for crushing. The moving balls and the race catches the coal between them to crush in the form of a powder, and this pulverized coal is then fed to the further process. In case of an impact or a hammer mill, there are swinging hammers that are connected to an inner ring and placed within a rotating drum. So as the coal is fed, the coal is pulverized due to the hammering action, and then it is further allowed to be used. This is very compact, low in cost, and however the maintenance is very costly, and then the capacity is limited. The power consumption also plays a role here, which becomes very high when the size of the coal required is too small. In case of a bowl mill, it consists of a stationary rollers and a power driven bowl, which where the pulverization takes place. You can see the complete setup in this animation. The primary air induced, so the air, this is the mill that is there. It is very similar to the grinding action. So there are grinding wheels or stationary roller wheels which do the required action. The next is the fuel burners. These burners are the devices used to burn the coal particles, which is done by uniform mixing of coal and air and creation of turbulence. There are various types of burners that are used: long flame, short flame or turbulent burners, tangential and cyclone burners. In the long flame burners or the U flame burners, the burner is placed such that the flame that is produced is a long U-shaped flame. The burner injects a mixture of primary air and the fuel vertically downwards into thin streams, which produces a long flame. The heated secondary air is provided at right angles, which creates the necessary turbulence, and this is very suitable for burning low volatile coal particles. In case of a turbulent burners or the short burners, these are built into the furnace walls. The flame is projected horizontally onto the furnace burning mechanism, and the primary air and the fuel mixture is combined with the secondary air and is then fed into the entry of the furnace. So the primary air and the secondary air combines with the coal, pulverized coal, and then is fed to the furnace. The velocity of the mixture at the burner tip is in the order of about 50 meters per second. The mixture burns intensely and the combustion is completed in a very short distance. Hence, the combustion rate is high, and hence it is also known as short burners. The next type of a burner is a tangential burner. In this, the burners are built onto the furnace walls at the corners. You can see here. They inject the air fuel mixture at a tangential tangent to the imaginary circle in center of the furnace, hence the name tangential burners. And as the flames intercept from each of these burners, they lead to a swirling action. This swirling action itself creates necessary turbulence, and thus it gives fast and high heat release rates. In case of a cyclone burners, these are burners which are externally attached to the furnace, and it resists pulverized coal carried by the primary air tangential in the cylinder, and there is secondary air that is provided also to complete the combustion, and there is some amount of tertiary air, so the third set of air in the order of about 5 to 10% of the secondary air, which is admitted axially at the center so as to move the turbulent coal air mixture towards the furnace. So you can see the cyclone action taking place here. The next is the liquid burners or the oil burners. It is the vaporizing oil burner, classified as rotating cup burner, and recirculating burners, wick burner. Then the atomizing fuel burners, and either subclassified as high pressure air burner or mechanical atomizing burner. Pause for a moment and understand or recall the difference between the vaporization and the atomization, and the next section should be easy to understand. In case of a vaporizing oil burners, the fuel at a low pressure is passed through a tube adjacent to the flame, which is before being released through an orifice. So the vapors of the oil, the liquid oil, is formed as a vapor and is then passed through an orifice. While passing through this hot tube, most of the fuel gets vaporized, so that the fuel ejected from the orifice is more or less a vapor. In case of an atomizing burners, the oil is divided into fine particles, which increases the surface area of contact with the combustion air. And due to this atomization process, a homogeneous mixture of the oil and air is produced, which is then fired into the furnace. In case of the rotating cup burner, the fuel flows through the tube in the hollow shaft. You can see here. And there is an electric motor or an air turbine that runs the shaft and the cup at high speed. So this is the cup which rotates at high speed, and there is a centrifugal force set up, and this centrifugal force splits the oil into small droplets, and there is air that is supplied as the primary air from the blower which is surrounding the cup, shown here in the blue, and this air aids for the combustion. In case of a recirculating burner, there is some amount of combustion products that are recirculated, hence the name recirculating burner. This high ratio usually needed to extinguish the flame due to increased proportions of the circulated products. In case of a wick burner, there is a cotton or an asbestos wick that raises the liquid by the capillary action. This is analogous to the use of age-old lanterns which were used in the earlier days. And there is air that is admitted through the holes in the surrounding walls, and this aids combustion. And in case of atomizing burners, the steam burners, the high pressure air or usually steam is made to enter through the nozzle here, and this mixes with the oil that is passed here in this orifice. The air and oil which is supplied to different channels are mixed, and then it is allowed to pass to the further process. In case of the mechanical burners, the oil is subjected to high pressure and atomized by passing through an orifice. The oil pressure that is developed is in the order of 10 to 20 bar. The oil usually passes through a swirl chamber and thoroughly gets mixed with the primary air, and the oil that is flowing through the orifice can be regulated using the help of a control piston, that is a plunger, which closes the tangential slots of the oil supply when it is required. So having understood how the coal is supplied, how the coal is burnt, we now look at how the ash is handled. Once the coal is burnt, it produces a large quantity of ash. The ash produced could be as large as 20%. In order to handle this, there is use of mechanical handling which becomes necessary. The ash should be discharged at a sufficient distance from the power plant. A breakup of the typical ash numbers that is produced. So here it is the maximum in the electrostatic precipitator, that the ash is extracted in the order of about 80 to 90%. So the ash handling could be either through mechanical handling, pneumatic handling, hydraulic handling, and which is further either low velocity or high velocity, and then steam jet handling. In case of a mechanical handling, the hot ash which is coming out of the boiler is made to fall over a belt conveyor through the water trough. So the water cools the ash, and this cooled ash is made to fall on a trough. This continuously carries the ash and is then dumped into the ash bunker, and this capacity is limited to about 5 tons per hour. The hydraulic handling is classified as low velocity and high velocity, and as the name suggests, it uses air mechanism. In the low velocity, there is water, which is the same mechanism as that of the hydraulic. The only difference here is the water channels are multiple. So there are two sets where the water is made to the ash, cold ash is made to flow through the sun. The capacity is better, relatively better, about 50 tons per hour. And in the high velocity, the water is sprayed, and as the ash drops in, the ash gets cooled and is then collected at the bottom. The water and the ash, cooled ash, drops subsequently to the bottom. The heat is quenched, and this ash is sent to the ash sump. The capacity, the highest, 120 tons per hour of ash. And in the pneumatic, the high velocity air picks up this ash and is then passed through the ash separator and then collected finally at the ash hopper and set. Instead of water, air is used as a handling medium, and the ash carrying capacity varies from 5 to 30 tons per hour. So steam jet handling, it is very similar to pneumatic handling, except that steam is used. There is an attempt to make use of steam. A jet of high pressure steam is passed in the direction of ash travel, that is conveyed in the pipe. The ash is deposited in the ash hopper. So this steam just pushes the ash that is coming out of the boiler, and then the velocity is given to the steam by forcing it to the pipe under the pressure little greater than the atmospheric pressure. However, the ash removal capacity is limited to about 7 to 10 tons per hour.